Algebra 1 students, welcome to today's 3.5 notes. This is the first of two parts. We're going to look at working with sets, and in this section we'll focus on roster form and set builder notation. It's kind of a strange little piece of mathematics. It's like learning the language of math, but it's important that we know that language so that we can communicate effectively. So that's what we're going to work on today. We will start with roster form. Roster form is when you list all the elements of the set within brackets, as you see in the example here. And one correction on this roster form, I just changed this word magically. It says brackets on your paper. Those are definitely braces, not brackets. Alright, the second notation we're going to look at also uses braces. It's called set builder notation. It's kind of a strange one, but it's actually very flexible. So it works for lots of different things. Roster notation or roster form only works when you have like a finite list, a list that that stops and starts at a given place, or that doesn't include every single value. Maybe it's only integers, maybe it's only odd numbers, something like that. But set builder, we could actually work with finite or infinite lists. And so set builder notation, it is written like this, and it's kind of a funny notation, but when it's x such that, that little vertical bar right there we say is such that, and then it's x is a natural number, and I'm just going to put a dot dot dot, but such that is what the vertical bar that you see right here tells us is representing. So in this case it was saying x is a natural number and x is less than 6. So essentially we're talking about natural numbers 1, 2, 3, 4, and 5. That's the same list as you see up here. Now the second example you see with set builder x such that x is greater than -5, that's actually an infinite list because, or infinite set I should say, because in that set it's not just integers, but it's actually including all the little values in between the integers. And I was just looking back at my handwriting. I don't think I've ever written an X sloppier than this one. Mark that down. Horrible handwriting from Hale. Good work. All right, let's take a look at these sets. Some of this will be familiar to you. We've talked about some of it briefly, but let's make sure we have this defined well. We're looking within the set of real numbers. Okay, that's the big set. Real numbers. Imaginary numbers you'll learn in an Algebra II class later on. We don't have to worry about those in here. Let's start with the innermost group, natural numbers. These are numbers that you learned when you were young. 1, 2, 3, 4, etc. Okay? We also call those the counting numbers. The whole number set, as you'll see, includes all the natural numbers, and it actually only adds 1 to the list. That one number, 0. So whole numbers and natural numbers are closely related, but the whole number set includes the number 0. Integers includes all the natural numbers, includes the whole numbers, and it also includes the negatives. So it includes numbers like -7, -6, -72, -813, etc. Okay, all these negative numbers would be a part of the group of integers. Okay, now we're getting to bigger sets, rational numbers. This set includes anything that we could change into a fraction, and I sometimes think of it as kind of a made-up word. Instead of saying rational, I think of it as fractionable. Could I change that to a fraction? So things that are fractionable, or perhaps they already are fractions, could be things like, how about 7/3 or -5/7. So or those are the ones in fraction form that aren't integers, whole numbers, or natural numbers. But sometimes we see them other ways too. We might see like 2.25, okay, a non-repeating, or excuse me, a decimal that either ends or repeats would be rational. Or maybe 2.3 repeating. The 3 repeating tells me that that's actually 1/3. 0.25 is 1/4. That takes us to the other group, irrational numbers. These are numbers that are in the decimal form, or they're non-repeating and non-terminating. In other words, they just keep going forever. You guys are familiar with some of these, like the number pi. If you don't know what that is, look on the wall in my room next time you're in here. A lot of square roots, like square root of 7 or square root of 2, numbers like that. Um, the square root of 4 or the square root of 9 are not irrational numbers. So why not? I'm going to let you think about that one and answer that one um, in class. If you have any questions, ask me. I'm happy to help you. All right. These next two slides basically walk you through what I just said. It's just laying out the definitions of what all these number groups represent. I'm going to kind of cruise through them, and I've already, like I said, I've already talked about them, so I'm not going to spend a lot of time right now talking about them again. What I will spend time talking to you about is examples 1 through 8. So let's get going here. Write each set in roster form and in set builder notation. Okay, so here it says that D is the set of integers greater than -5 and less than 5. All right, so let's do this in roster form first. For roster form, we'll open our braces. Integers greater than -5, that would be -3, -2, sorry, -4, -3, -2, and so on. And that list stops. And actually, I'm going to abbreviate this. I'm going to do this and then say that it stops at 4. Use a little shortcut there to save a little writing space. Okay, for set builder notation, it would look like this. It would be x such that -5 less than x less than 5, and then we would also need to put x is a natural number. And actually I said that wrong. It's not natural, it's an integer. Some of them are natural, some of them are not. All right, so that set builder notation can be a little tricky, but you'll get the hang of it. Okay, number 2, T is the set of odd natural numbers less than 14. So roster notation, we'll start with that. Odd natural numbers less than 14. That's going to be 1, 3, 5, 7, 9, 11, and 13. Those are the odd natural numbers less than 14. For set builder notation, we would say x such that x is less than 14, and we could also say x is an odd natural number. So this set builder at times requires us to use some words. It's not just mathematical notation. All right, why don't you give number 3 a shot on your own. So pause the video, watch number 3, or do number 3, and then see how your answer compares to mine. All right, welcome back. You can see my answers on number 3. This one was a little tricky perhaps. Factors of 18, you can see my roster notation. You do 18, 36, 54, and then you use the ellipsis or the 3 dots. Okay, so the 3 dots mean that that pattern is going to continue. All right, set builder on this one, we said x such that x is equal to 18z. And what I did there was also noted down below, z represents the set of integers. That's just a shortcut. We could just say in words, you could say x such that x is 18 times an integer value. Something like that would work as well, but I think I like what I did here, so I'm sticking with it. All right, so let's actually use this to answer some questions. Write the solution of each inequality in set builder notation. So I'm going to do the algebra pretty quickly here. 4b is greater than or equal to -20. We of course need to divide by 4. So b is greater than or equal to -5. Okay, so to answer this, to put this into set builder notation, we would just simply say b such that b is greater than or equal to -5, and it's not restricted to be integers or any other particular number set other than just it needs to be more than -5. Again, my handwriting is failing me this morning. Apologies. All right, let's look at number 4. Again, it's really just a little practice working with inequalities. So we'll go ahead and distribute first. Then we'll have negative p minus 10 is less than negative 2. I'm combining like terms. I need to add 10 to each side, so negative p is less than 8. And then we'll divide, or you might think of it as multiplying, by negative 1. So p is greater than, remember to switch that inequality, negative 8. And again, our set builder notation would be something like this. P such that p is greater than negative 8. Pretty simple when you think, I guess when you think about it. It's just a new notation, a slightly different way to answer the question. All right, so let's take a look at number 5 here. Negative 2x minus 14 less than equal to negative 14 plus 2x. If we add 14 to each side, we'd have negative 2x less than equal to 2x. Let's subtract 2x from each side, so negative 4x less than equal to 0, and then divide by negative 4, and remember you have to switch that inequality, so x is greater than or equal to 0, and then again we're going to go to the set builder notation, x such that x is greater than or equal to 0. Alright, go ahead and pause the video. You guys do number 6 on your own. Alright, welcome back. You can see my work on number 6. The solution being x such that x is less than 1/3. Remember that you do divide by a negative here, so you have to switch that inequality. We divided by negative 6. And I think you can probably follow the work other than that. Alright, let's take a look. This is our last slide. We're there. Alright, so let's write each set in set builder notation. So we're changing from essentially a roster to a set builder. Okay, so here we go. This is the set B. So what I'm going to do is say set B is equal to, or really I've been leaving that out most of the time, and I'm just going to leave it out here. I'm going to say x such that x is greater than or equal to negative 3. That's the first thing we see. It starts at negative 3 and moves upwards. But it also is there's another restriction there. It's not every single number, it's just integer values. So we could say x is an integer. That would take care of the fact that we're not doing numbers like negative 2.5. Okay, let's look at number 8. On this problem, our set is finite, so it has only 5 terms, exactly 5 terms in it. And I'm going to do it this way. I'm going to say x such that x, let me try that again. We'll do 2, we'll do it that way, less than equal to x less than equal to 10. That takes care of starting at 2, stopping at 10, but we also would need to say x is an even number, or integer if you prefer. Okay, why don't you guys give it a shot on this last one. Alright, so pause the video. When you're finished with it, hit play, compare your work to. Alright, welcome back. I know number 9 was kind of a weird one. This is probably not the best one to have on your own, but if you were looking at it and saying, what do I do with that? Don't worry, you probably weren't alone. Essentially what these numbers all have in common is they're all the factors of the number 18. 1, 2, 3, 6, 9, and 18 all divide evenly into 18. So we can say x such that x is a factor of 18. Alright, again guys, it's kind of a strange topic. I don't want you to be in a panic if this is a challenge for you, or if you're like, I just don't understand that part of it right there, Mr. Hale. I get that, okay? So we'll keep working on this, try to figure out the basics of it, and then when you come to class, we'll get to work. You guys have a great